just want to say, feel free to interrupt me at any point in time. I'm happy to go into unrelated topics like SRE stuff or WGU at any point in time. So, or anything around the presentation. So just let me know. Um, Personally, I've been using Linux for over 10 years. I think I first installed it in 2012, really old version of Fedora back then. I think it was even before Systemd. But professionally, I've been doing it for closer to 6 years. And I've been a senior site reliability engineer at Shippo for a little over 2.5 years now. Shippo's a startup. We are like a marketplace for purchasing shipping labels and doing all kinds of stuff around shipping. Before that, though, I was a platform engineer and a SRE at CSA Insurance Group. I spent a lot of time working with Scott. Scott ended up taking my old position on the platform engineer team when I left there and joined the SRE team at AAA. So, yeah, I'm happy to go into anything around SRE stuff. If you guys have any questions about that. I have 19 IT certifications, including the Red Hat Certified Architect. It's just something I kind of enjoy doing in my spare time. Really got to get back on the track of doing the AWS ones. I think I only have 4 of those at this point, but I'm going to be going for the AWS machine learning specialty at some point in the time in the near future. And I'm a recent graduate from WGU's Bachelor's of Science Computer Science program. I know there's a few other people in the Discord, although I don't remember exactly who are in these or in this program as well. Or thank you, or attending WGU. So I'm happy to answer any questions about the program and some of the stuff about it, whatever I can talk about. And I will be demoing my capstone project that I did at WGU at the end of this, just because I know a couple people have mentioned wanting to go into that. So to get started on this talk, we're going to be going over what exactly is the eBPF and what makes it useful. And our outline is really just going to be introducing eBPF, a little bit around the usage of it. We're not going to be going too much into the weeds on this because it's a pretty in-depth thing. I just want to show some high-level stuff around it. And then I really want to get into the industry usage and case studies around it because it's an important emerging technology. I think we're going to see a lot more companies and startups who are heavily involved in eBPF and build tools on top of it. We're already seeing a lot of that out there, but it's good to be in the know on these kind of things and know what kind of problems people are solving with it and what it offers over traditional technologies. Okay, so introducing eBPF. What exactly is eBPF? It is a technology in the Linux kernel that allows user space code, which is pretty much everything, all of your applications, pretty much everything other than the operating system kernel itself. It allows these to run custom code within the kernel. And this is a really new feature because on pretty much every other operating system, the only time you're doing anything custom within the kernel is if you write your own driver for it. And that's a rather painstaking process with a lot of volatility around it. So we'll be going over how eBPF makes this a lot easier. eBPF programs are event-driven, and for those of you who aren't familiar with event-driven patterns and like JavaScript and a lot of other things, this means that they run when certain events occur within the kernel. So your eBPF programs can be hooked up to run on like disk input-output operations. When network packets are sent and received, you can actually like hook an eBPF program onto just about anything that happens within the Linux kernel. So that functionality has resulted in a new generation of tooling for debugging, observability, networking, security, and probably some other use cases I haven't listed here. So I borrowed this from the eBPF official website. It just kind of goes over some of the high-level capabilities of it. Around networking, you can speed up the packet processing of whatever you want to process on a packet, whether it's observability, whether it's DDoS detection or firewalling. You can process these packets without leaving kernel space. And we'll be going over that a little bit more and what that means in the next slide. It's easy enough to add additional protocol parsers and program any forwarding logic, if you're trying to implement a load balancer or other capabilities. Observability and tracing and profiling are probably the biggest wins in the eBPF space, just because you can write a program that hooks into any event that occurs within the kernel. It makes it really easy to aggregate metrics that you wouldn't normally have access to, whether that's exact information on disk input output or events happening within the kernel, system calls being made. It really opens up a whole new realm of things that you can do and with a lot lower overhead than traditional solutions. Tracing and profiling, it's again, like I mentioned, it's really easy to have an eBPF program that is set up to occur or that's set up to run whenever a certain event occurs. So, like whenever a file is read, you can have a program that runs real quickly in the kernel and collects some sort of information around it. So, you get really unique and powerful introspection abilities by using this. And finally, security. There's a lot of stuff going on in the security space with eBPF. You can see all of what's going on with the network packets coming in and out of the systems. You can see what's going on with all file reads and operations. So you have the ability to respond to things in real time rather than collecting info or running scans or a lot of traditional approaches that just don't have the same visibility and insight that an eBPF program would have. Can I give real world implementation and tools? Yes, actually, I'll be going over this a lot later on in the slides. We have several industry use cases from Netflix, Facebook, and CrowdStrike, Cloudflare. And is it similar to system extensions with Mac OS? Kind of. So system extensions are, I guess they're more like a driver in that it's actual code that's tied to a kernel API. So it's a little bit less flexible and a little bit more cumbersome to install those. So we're going to go over how eBPF differs from traditional things like this. It's a lot more dynamic and portable across kernel versions. So we're going to cover what exactly is kernel mode and what's user mode and how are these different. So kernel mode is a privileged mode of operation for the CPU. This is where your operating system kernels is run, and basically it has direct access to all the hardware memory on the system. It can exit privileged CPU instructions that normal programs can't handle or can't execute without crashing. And that's things like controlling devices, seeing memory outside of like page memory or virtual memory. Handling interrupts is a big one here. And an interrupt is like something asynchronous that happens within the operating system. So like if you issue a read request to a disk, or if you send a network packet and you're waiting for it to be received, an interrupt is kind of like when the CPU gets notified of an external event. So pretty much nothing else runs in kernel mode except from the kernel, but eBPF kind of opens the ability for us to do custom stuff in kernel mode without writing a whole device driver. Pretty much everything else runs in user mode, especially on Linux, and that's a non-privileged mode of operation for the CPU. And what that means is that user mode applications just have access to their own subset of memory. If they were to try to access memory from another process, they would crash. If they try to access invalid memory that's just not assigned to anything, they would crash. And they can't execute non-privileged instructions. So again, this includes every application that you run outside of the kernel and driver. So if you're using Bash on a Linux system, that's user space. If you're running Firefox, it's user space. Even like X11 and Wayland and all those desktop application services, those all run in user space on Linux. Just answer some questions real quickly. New generation IP tables. IP tables is kind of user space programming in the kernel. To answer your question, Taki, we have a use case at the end of this from Cloudflare about how they tie into IP tables with eBPF, and there's a whole article on how they do that. So we're going to go into that. But eBPF is still separate from IP tables. There's a lot it can do for network processing and filtering and dropping packets, but it really goes beyond just those capabilities. Marcus Hitchson was explaining why Microsoft still allows access to kernel, which led to the CrowdStrike issue. There's a lot of reasons about that. Funny enough, I have a slide at the end of this about how CrowdStrike incident on, I think it was July 19th, that probably could have been avoided if they were using an eBPF-based program rather than a traditional driver. But yeah, there's a huge issue with any driver loaded in any operating system, and that's because it's just entirely arbitrary code. eBPF is more of like a sandbox within the kernel, which we're going to get into in a few slides. So the worst that it can do is consume too much resource usage. It can't crash your kernel. So there's a lot of safety features built in from that. And for Scott's question, yeah, we're going to be going into Falco a little bit on one of these slides. And Trevor asked, does eBPF interact with the kernel ring buffer? That's actually a good question. I don't have an answer to that off the top of my head. I don't think so. It has its own buffers and maps and lots of other data structures it can share with user space applications. I don't know if it directly acts with the kernel ring buffer. It may be able to trace onto events that happen in the kernel ring buffer, but I'd have to double check. Okay, so as a high level overview, there's a number of components around eBPF. There's eBPF programs, and this is small pieces of user defined code that run within the Linux kernel. They pretty much run in a virtual machine. It's probably the best way of calling it. I wouldn't go as far as to call it a sandbox because it does have access to a lot of things. However, it's still a very isolated piece of code. If your eBPF program crashed or tried to access invalid memory, there's a lot of safeguards around that to prevent it from happening in the first place or to mitigate the effects if it did happen. And that's all done through what's called the eBPF verifier. So before your eBPF programs are ever loaded into a kernel, the kernel will, at runtime, verify your program. We'll get into that a little bit more, exactly what it checks for. But basically, it's a safety guard to check things that we could never check with the driver. We can check to make sure they're accessing valid memory, that they're not going to get stuck in any loops. And again, we'll get into later how this could have presented the CrowdStrike issue from a few weeks back. eBPF has a concept called maps, and I mentioned that these are key value data stores that eBPF programs use to store and retrieve data, and it allows them to communicate between kernel mode programs and user applications. The term that they use is called maps, but really there's a lot of data structures that eBPF provides. You can do more like traditional arrays. You can do buffers, least recently used data structures. There's some per CPU stuff going on there. But for the most part, in most use cases, an eBPF map is just like a key value data store. You know, you have maybe like a process name as the key and then some metric you want to store for it as the value in them there. And this allows the program to keep track of its own state, but it also means your eBPF programs, which again run inside kernel mode, they have an easy to use data structure that they can share with the user mode application. So your eBPF programs are kind of broken into two parts, one that is generating data within the kernel and another one that's consuming it outside of there and giving you, whether it's security information, monitoring, tracing, whatever you're trying to collect, you have a data structure to store and access between them. Finally, there's the eBPF JIT compiler. This stands for just-in-time compiler. So all of the eBPF programs that you write, they're compiled into something known as bytecode. This isn't actually the machine code that your processor can run directly. For those of you familiar with C, C++ languages like that, Rust, Golang, a few others, those all compile into native code, and that's like whatever your CPU directly runs. So if you're using an Intel or AMD processor, that's usually x86-64 instructions. I'm on a MacBook with ARM, so that's ARM 64 instructions. But compiling to bytecode gives eBPF a couple things that it can do that are special. The first is it allows the verifier to go through and check and make sure that the program's going to be safe before it actually loads it into the kernel, because anything running in your kernel is both a system stability risk and a security risk because it has access to everything. It can see everything in theory, so you want to make sure it's loading safe code. And you also want to make sure that it's not going to crash your system if anything bad happens there, because again, if you're running in kernel space, you have the ability to take down the whole system pretty easily. So using that bytecode means that it's going to be run through a verifier before it's ever loaded. That's a great thing for safety and stability. And it also means that eBPF has a compile once, run everywhere approach. So you don't have to write a specific eBPF program and compile it for ARM and then compile it again for Intel and PowerPC and all those other architectures. You just distribute the bytecode and the kernel will take care of converting it into native machine code for your system so it runs with optimal efficiency. And that's all done transparently. It's not something you ever have to worry about when distributing programs. So I mentioned the verifier earlier, and this is the first place that your eBPF programs are loaded into before they're ever running in the kernel. The verifier validates that the programs are safe to run, and it's more checking around safety in terms of stability and making sure it's not doing anything. It can't verify that you're loading safe code. Always check the author and reliability and trustworthiness of whoever you're running code from, especially within the kernel. It could be doing something malicious. But it checks for infinite loops. You want to make sure that the program terminates. It doesn't go on forever. These are supposed to be quick programs that run, again, whenever a network packet comes in or whenever a file's open. So you're really just kind of collecting some data and exiting within your eBPF program. It's not supposed to sit there and pull anything. It's not supposed to have any weird conditions. You can use loops. You just can't have ones that don't have exit points or have like complicated logic within them. It also checks arbitrary and yeah.
Real quick, I was just going to say, I'm going to quack every time somebody asks you a question, just so you know.
Oh, thanks.
Just in case, just so it doesn't, I don't want you to be running along and go like, oh man, what was he asking or whatever.
So King Buns, you asked if eBPF runs in a virtual machine. Not really, but it used to, and there might be some architectures where it still does. So the just-in-time compiler takes care of turning that portable bytecode into native machine code. And off the top of my head, all major architectures do this. They do this for a lot of efficiency reasons. I mean, anything running in the kernel is going to impact the performance of your entire system and every application that runs on top of it. So it's really critical that it's running as fast as it can, and machine code is pretty much always faster than a virtual machine. In the past, I want to say it was 2014 this was introduced. I could be wrong. Maybe it was a little bit later. But before then, the bytecode actually did run in a virtual machine. It's a pretty simple instruction set, so it's still very high performance. The bytecode for eBPF was designed to be really similar to most machine architecture, so it's easy enough to translate it one-to-one to assembly code. But as far as I know, again, it's not really running in a virtual machine. It's more of a sandbox, not in a full sense, but it's more similar to that than it is to a virtual machine. So it's not being like interpreted like a Python or Java program would be. It would be more like Java with JIT compiler. If that makes sense. Thanks for the quack, Scott. Appreciate it. All right, so yeah, we already mentioned the verifier checks for infinite loops. It also checks for arbitrary or invalid memory access, so you can't just put random pointers in your source code or try to dereference null or anything. It actually has pretty good checking for anything that could cause invalid or arbitrary memory access, and also uninitialized memory. So eBPF programs are written in a language that's very similar to C. It's basically C with a couple small extensions to it. And it can, for those of you who are familiar with C, if you just create like an empty structure or something, or just declare integer or a floating point variable, and you don't initialize it to anything, it's just going to have random memory content in it. So that's pretty unsafe, and eBPF programs are guaranteed to be checked for the use of uninitialized memory before they're ever loaded into your kernel. Finally, it checks for deadlocks. So this is just static checking, and because there's really simple loops in eBPF, it works well. I don't think there's any conditions where you could really write code that would generate a deadlock without the verifier realizing it. But basically, whenever you're using something that locks a data structure, whether it's a mutex or a spin lock, for those of you kind of familiar with multi-threaded programming or heard of that or worked with those before, anytime you're locking a resource, you want to make sure you unlock it when you no longer need to lock it. If you don't, the next time the code tries to run, it's going to be waiting for you to unlock something that you're never going to unlock. So this prevents a lot of cases where an eBPF program could bring down the kernel with it, or just freeze your entire system because it's waiting on an event that would never happen. So the eBPF verifier, as I mentioned earlier, it checks the bytecode that you compile to, not the source code. So if you change compiler settings on an eBPF program, that could affect whether or not programs are accepted by the verifier. So just something to keep in mind. It's not a perfect process because this could change slightly kernel to kernel as well. But for the most part, most eBPF programs are really simple. They don't do a whole lot of loops and don't need to. You shouldn't really run into this problem unless you were like a vendor writing a tool based on eBPF. All right, so bytecode and the JIT compilation process. Already went into these a good amount, but it's just a portable bytecode format. It's similar to a simplified assembly language. And after it's been verified by the verifier, it is compiled into native machine code. These are pretty small programs, so compiling it doesn't take very long. It doesn't have much latency when you're loading an eBPF program, and it means that every time it fires off after that, it's going to be a lot faster than if it were just bytecode. And as I mentioned before, this allows programs to be distributed for any Linux system. If you were writing a traditional driver, which is like a piece of code that's not part of the kernel, but it still runs in kernel space, if you're writing one of these, you have to compile it for every architecture. You have to make sure it's going to run on the target Linux system. The Linux API in the kernel changes every release in some way. It's not guaranteed to be stable at all. And if you've ever run a Linux system with an NVIDIA GPU and tried installing proprietary drivers, you probably run into something before with some sort of kernel dependency error because the whole driver interface can change release to release. So eBPF programs are a lot more portable. You do have to keep in mind that if you're like hooking to a specific event that occurs within the kernel, that might just be something that's not happening or available on every single kernel. So you still have to know a little bit about your target system in some cases. But for the most part, this makes distributing eBPF programs a lot simpler than writing a driver for every different version and compiling it for every architecture that your users might be using. So a quick history of eBPF. In 92, there was something called Berkeley Packet Filter, and this was on Unix. I actually don't know what Unix system this originated on. I tried looking that up and I couldn't find it. It's Berkeley Packet Filter, so I'm assuming it was BSD Unix. But this was just network filtering. There wasn't a lot of advanced capabilities. It couldn't do anything outside of network packets, and it really just ran on like specific events. So it wasn't a very flexible technology. But in 2014, eBPF, which is extended BPF, virtual machine was introduced to the Linux kernel to support this. Earlier, somebody asked me, or I mentioned whether or not it runs in a virtual machine. So I guess as of 2014, it was running in a virtual machine. Later on, the just-in-time compiler was released for this. So this improved performance and functionality and capabilities over eBPF. And it really made it into the tool it was today. Berkeley Packet Filter is really only used by like some networking tools in the past, and it didn't really have the same capabilities that similar tools and for tracing would ever have. In 2018, a tool called BPF Trace was released, and this is a high-level language. We'll be demoing this a little bit later on. It's very similar to dtrace, to those of you who have worked with Solaris or FreeBSD or any other operating system that has dtrace on it. But basically, it's just a way of using a command line tool to do some quick queries. You can check a lot of things with BPF Trace. It doesn't have to be a small program, but for the most part, it's more of an ad hoc debugging feature rather than like a whole program that gets loaded on. It's more useful for system administrators, looking into performance issues or running performance tests and benchmarking systems. In 2022, Microsoft actually released eBPF for Windows, which is just like Linux eBPF, but it runs on the Windows kernel. I haven't played around with it yet. It seems like a really interesting technology. Microsoft seems to be doing some work around it. And it's exciting to see because Windows drivers have had plenty of stability incidents like the CrowdStrike incident recently. And it'd be interesting to see what Microsoft does with this and if they could really get past using drivers for a lot of these capabilities. So similar technologies, as I mentioned earlier, there's dtrace. This was kind of the pioneering tool around tracing anything kernel level, whether it's files being opened or certain system calls happening. And this was introduced by Sun Microsystems for Solaris back in 2003. It is available on several other operating systems, including Mac OS, FreeBSD, and Windows. They actually have eBPF and dtrace available at this point. It's not as powerful as eBPF since it's really just meant for tracing. It's not like a full kernel execution environment where you could drop packets or respond to auditing events or security events. It doesn't communicate with user space in the same way. It's really just around tracing and performance insights. There's also something called DT. It's a newer tool for OpenBSD, a really interesting but not widely used Unix system. It's really just like dtrace. It's just a dynamic tracer. So that gives it a little bit of similarity to eBPF for like the BPF trace use case, but it's not full fleshed out technology like eBPF. Okay, so using eBPF, this is where we're going to get a little bit more into detail. There's a whole toolkit around creating eBPF programs and running these, so we'll give a brief overview of these. The most commonly used one, and the one you'll see in most examples, is BCC, which is the BPF compiler collection. And this is the toolkit for creating efficient kernel tracing manipulation programs. You can really write any eBPF program using this framework. And most importantly, this gives you the ability to write eBPF code in Python. Your actual part that runs in the kernel, that's still in the C-like language, but you can do the rest of your program and interact with your eBPF maps using Python, which is really useful when you're getting started. And this package, which you'll find on, I think, every Linux distribution at this point, it also provides several tools for system monitoring and debugging, and we'll take a brief look at that as well. Those as well. And basically, this is just like pre-written tracing scripts and some other stuff it's good to have on hand, especially if you're a system administrator or doing a lot of performance testing. So the lower level ways of interacting with BPF programs are libBPF and eBPF Go. And these are C-level libraries for not only writing your eBPF program that runs in the kernel, but also loading it and doing whatever else you have to do with it outside of the part that runs in the kernel. And eBPF Go is from Cilium, which is one of the really popular tools around eBPF now. We'll be looking at that later on. And this is the same exact thing, but it's just for Golang specifically. BPF tool is something for inspecting and interacting with eBPF programs and maps. So you can see all the programs they have running. You can see what data structures they're using. You can see what specifically you can interact with on the kernel that you're running on your system. We won't really be going into this one as much because it's really not as interesting for demonstration purposes, but it's a good thing to have on hand. And at the end of this, I'll have some links to articles and books where they go a lot more into tools like this. Finally, this BPF trace, we mentioned this earlier, it's really just a high-level tracing language and command line tool that's really similar to dtrace. Earlier, in the last slide, I mentioned that the BCC tools package, the one that lets you write programs in Python, this comes with a whole suite of really useful tracing utilities right out of the box. So if you're a system administrator just looking to do some performance tests, you probably never actually have to write your own eBPF program. You could use one of these many tools available in this package. A lot of these are similar to their non-eBPF counterparts. Scott, you probably use this, but like ext4 slower for testing file system performance. A lot of these are really similar to existing programs, but they use the eBPF interface. Some of the other ones in here, I think like at host latency and exec snoop, those are more unique to eBPF and give you some insights you might not have before. Okay, so BPF trace, I already talked about this a couple times, but it's high-level tracing language for eBPF. And you can do all kinds of cool stuff in here. You can write scripts that will give you histograms and counts and averages and other data aggregation techniques. So rather than having to write a whole program for it, if you learn the syntax or a similar tool, even better, you can get right into it. But you can do some really interesting profiling just with one command line tool. It's really like a Swiss Army knife for most use cases around tracing. So just like any eBPF program, you can do all kinds of dynamic instrumentation and hook into kernel events happening on your system without ever having to write a custom driver or modify your kernel or even reboot, which is great. It's useful for ad hoc monitoring, debugging, profiling, and even security auditing. Like if you want to keep an eye on what files are being opened on your system or what network connections are being established in and out of your system, you have a really good insight into being able to do this with just one tool. So a couple examples, and I'll be running some of these later, but this is just like what the syntax looks like. Pretty much any BPF program you're going to have to use as root on your system because it is interacting with the kernel. There's always security concerns around it. You as a regular Unix user, you can't just load any arbitrary code you want into the kernel, which makes sense. So for pretty much all these use cases, you'll need root capabilities, but this is just something that whenever the open at function, which is like whenever you open a file, this is eventually the system call that's getting used on the Linux side. So whenever this function's entered, whenever any process on the system is calling open at, which again opens file, it counts when the function started. And whenever this function is exited, we can calculate the latency of when it started versus when it stopped. So in other words, how long it took for the function to run. So without ever having to modify the kernel or touch any drivers, we're able to automatically add profiling to see how long this function's taken to run every time. And we get a histogram output afterwards that shows us more information on it. And another simple one, you can do this with 100 existing tools, but it's kind of cool to be able to do it with BPF trace. You can get a CPU usage distribution per thread ID to see, which threads running on your system are using the most CPU usage. And you'll see you actually give it the frequency you poll at. So this would be 99 times a second. And you can put really whatever you want in here. You get that flexibility right within the tool. Tripwire with eBPF would be nice to have. Yes, it would. We're going to go into some tools that can do some pretty similar stuff. So it's really interesting to see what's going on with the security space in eBPF right now. All right, so here I've SSH'd into a Linux system, just OpenSUSE virtual machine running on my desktop. And we're going to look at a couple examples of using BPF trace. So this one's going to print process names along with the files that those processes are opening. So in other words, we want to see what every program on our system here is opening in real time. And with a little change in syntax, if you wanted to change this to monitor just one process, it'd be a really trivial change. So we see already there's a process called hierarchy balance. This is something at the Linux system level, and it's opening a couple files right now. Systemd is doing stuff. So there's a lot of background processes accessing things. Now, I don't know if you guys can see this screen or not, but I have an OpenSUSE virtual machine on the other screen, and I'm just going to have it cat a file.
We can see it.
Yep. And you'll see cat doesn't just open this one file. It opens, I was using a file called ringbuffer.py. It was just an example BCC tool. And so we see that cat opened that file, but before that, it actually opens a whole bunch of locale stuff. And it even loads the dynamic libraries that the program needs to run. So in real time, we get access to all this stuff. I've had plenty of cases where I've both been curious what processes are opening files and what specific files a process is opening to see where it's crashing or something. So say cat was crashing and you don't know why, and you think maybe it's something to do with the file that you're trying to run. You can see that it stops off earlier on. Maybe it ran into an issue in one of these locale files that you didn't even know it was interacting with. So having this available in real time, just using a quick script, is really useful. If I say refresh a page on Firefox, we're going to see a few things that were loaded in the back. It's opening cache files. It's looking at something to do with its own mount points. So it's really interesting just to see what a process is doing all the time. I mean, I'm not even interacting with the system right now, but it's still opening files constantly. So that's a useful one. Take a look at comments. So here's another one. We want to make a histogram to see what kind of message sizes, so like network packet sizes, are going on within the next 10 seconds. So I'll run this a couple times just to show you guys. I'm just going to reload a web page in a few ways here. Okay. So this only was running for 10 seconds because we set an interval parameter on it. I've got some links at the end of this to all kinds of stuff around BPF trace if you guys want to learn more about the whole syntax and what you can do with it. But we get a histogram here showing the range of sizes of all the network packets that were open. So maybe we're curious, like for performance testing, are we dealing with a lot of small packet sizes or are we dealing with a lot of large ones? And what we want to know is, maybe how we want to tune our system to accommodate our standard use cases and such. So with just one quick script, we're able to get some insight into the overall average size of packets that we're setting through the system and get a visualization of it. So that's really useful to figure out what's going on. Oh, histogram doesn't mean bar chart. Yeah. I wrote histogram, but it technically is using the histogram argument in here. But yeah, it's not the same as the visualization. I think I had one other in here. So I mentioned the word system call a number of times. I figure a lot of you are probably familiar with this already, but a system call is whenever a program calls into the kernel for anything it needs to. So if it wants to send or receive network packets, it's got to go through the kernel. If it wants to open and close files, it has to go through the kernel. So we can see by process ID or by process name how many syscalls different programs are running. So again, I'll do a couple things over on Firefox. Run a couple things in the command line here. We'll exit out of this and we'll see the number of system calls that every process made during the time that we were running that. We'll see Firefox did a ton of these. There's also something called glean.dispatche, probably a background process of some kind that did a lot. X.org, so our graphics / desktop layer, called the desktop server. Just gives us really interesting information to what's interacting with the kernel the most. And I mean, we were mostly working in Firefox. That makes sense. That's near the top here, and that's probably a related process that works with it. Can we keep a recording of this? Scott, actually, I don't know how the recordings on this work.
I missed starting it, so it's fine. We'll probably just figure it out. Maybe Pessa, maybe when you come over and I have you on as like a guest, maybe I'll just have you talk through it again. What do you think?
Absolutely.
That would be like a Twitch YouTube thing then.
Definitely. I have all the slides for this after, which I'm happy to put up, and there's some books, including a free ebook that I use for a lot of this presentation, and a lot of articles at the end of this. So there's plenty of resources for you guys. I'd be happy to record them again in the future.
There's also a Google thing that Rodon put together, so people can put if this is their favorite talk.
Sweet. So industry usage. This is where it gets really interesting to me. So I'll be honest, in work right now, I'm not really using anything that relies on eBPF except maybe a tool called Sysdig. I don't know if we have that functionality enabled or if we're even on the latest enough version for it. But there's so much going on in the space. I know there's a lot of interest on my team. I know there's a lot of interest among lots of people, software developers, SREs, DevOps. And a lot of this tooling is built around Kubernetes. So it's modern from the get-go, and it's exciting to see how it's already found such interesting use cases. Yes, Scott?
That wasn't me. I'm on mute.
Oh, sorry. So Cilium. If you guys have heard of any tools around eBPF, this is probably the one you heard of first. It's definitely the one I heard of first. And it's open source software that uses eBPF to enhance network security and observability in Kubernetes clusters. For those of you who know a little bit more on the Kubernetes side, it's a CNI provider. So it's basically like the underlying infrastructure, software level infrastructure that your cluster can use for network communication. Because it uses eBPF, it's very high performance, and we'll get into a little bit more why later. And it offers features such as service discovery, load balancing, and direct pod-to-pod communication. So by using eBPF, it provides deep visibility into network packets, something that you really can't get from traditional tools. Even those of you who have used things like Perf on a Linux system, it's not nearly as flexible in terms of what it can attach events to and such. So for everything eBPF is capable of, Cilium uses it for. However, like we mentioned back in the verifier section, there are some limitations on what can actually run in the kernel for safety reasons and stability reasons. So for some things like layer 7 network processing, it still uses another technology called Envoy, which does a lot around Kubernetes networking. I won't get too much into that. And there's also observability that Cilium provides, and it's very lightweight in terms of collection. And this gives you information on service maps. So like if you have a bunch of microservices, say you have like an e-commerce app and you have like an orders service and a login service and a payment service, you can see what services are talking to each other, what kind of messages they're sending, what kind of endpoints they're hitting. And Cilium can collect all this automatically because using eBPF, it can just see what's talking to what rather than having you figure out what exactly you have to monitor on your endpoints. So this is one of the bigger ones around networking. I also find it really interesting what Falco's doing. It's a cloud-native security tool for threat detection, regulatory compliance. And it's probably one of the closer things to Tripwire on eBPF right now. It uses eBPF to employ custom rules and kernel events to detect anomalous activities in real time. So basically, it can find usage patterns in what a system's normally doing.
Oh,
Oh,
cool.
sorry, one more time on that question.
Do you want me to call it?
And make sure you
Sure.
guys are on mute.
Okay. Yeah, if you guys have any questions, just feel free to drop it in the chat. eBPF is used by Falco to employ these, anomalous activity detection events in real time. So basically, rather than having to use legacy tools to figure out what's going on, a lot of which like detect activities in batch. If you've used auditd on Linux, that's something that can detect file changes, but it updates a database to do so. It's not as real time as something that can just see what system calls are being invoked and what process they're invoking them and look for abnormal activity. So you can set it up to monitor unexpected file access, unexpected network connections, privilege escalations. Maybe it sees a user who's never run sudo on a server before and it detects that for the first time, or somebody who's never run it before and it's escalating on a bunch of servers at once. And that's great for traditional Linux system administration capabilities. It's not just a Kubernetes tool, but it's also available on Kubernetes as well in a way that integrates with it pretty well. And finally, Pixie. This is actually one of the ones I've looked into, although we're not currently using at work. But it is a open source observability tool for Kubernetes, originally created by New Relic, but they donated it to the Cloud Native Computing Foundation. And that's the foundation that does a lot of stuff around cloud native tools and containerization tools, Istio, Kubernetes, Grafana, a whole bunch of other things. Prometheus is a big one. Those are all part of the Cloud Native Computing Foundation. And Pixie uses eBPF to automatically capture telemetry data, such as the easy things like CPU and memory usage, network latency, and most importantly, application performance metrics. For any of those of you who have set up monitoring on a service, it's really a pain to have to go into your code and configure all the different endpoints that you want to monitor and configure where you want to track latency and where you want to capture specific performance events. Pixie can use eBPF to gather all of this information automatically. I mean, you get the insight to see like what processes in your application are calling into specific kernel events. So you can see where most of your network connections are coming from. And you never have to use any application instrumentation here unless you're trying to do something really unique. eBPF can provide you so much of this out of the box. And again, it's great for low level or low performance collection of CPU and memory usage and all those other things you get out of standard monitoring tools. So I wanted to go into some case studies around some use cases of eBPF in the industry, some more concrete things. So I picked 3 of these I wanted to cover. For network monitoring, there was a use case for Netflix where they needed scalable and performant solutions to monitor the network performance across all their infrastructure and microservices. Netflix is a really complicated infrastructure. I mean, they have their own edge nodes, they have their own compute. They also have most of their stuff in AWS, I believe, and they have their CDN and content restriction stuff. So there's a very complex infrastructure they have. Plus, they're a pretty heavy user of microservices. So again, for those of you who don't know, rather than having just one big application at your company for, say, like a e-commerce website, rather than having just one instance of an app that takes care of all your requests, microservices are where you break it up. So you have like one application that handles payments and one that handles orders and one that handles user login. And all of these communicate with each other, and that kind of lets teams work on things more independently. So Netflix and a lot of other big companies are moving this way. They want to make sure that teams can move at their own scale and that there's not just like one single place where all of their applications are defined. So microservices are great for that, but monitoring them gets a little bit complicated because all your services that need to talk to each other are talking to each other. So rather than trying to figure this all out manually, Netflix developed a tool called Flow Exporter, and this leverages eBPF trace points to capture TCP flow and data in near real time, and it does so using less than 1% of CPU and memory. Again, for any of those out there who have monitored systems or worked in observability or monitoring or production support, you know that adding monitoring to a system can actually slow it down significantly. It can result in a lot of other performance problems that you didn't have before. So sometimes even trying to look into a problem generates more problems. So being able to capture this information about detailed network communication access between services with less than 1% of CPU and memory usage on an instance, that's a really big deal. That's cheaper compute for them because they get a speed where they don't have as much overhead from performance gathering. But more importantly, that means it's not impacting services and it's not leading down, problems with the network collection itself. That's not slowing them down. So with that, you get real visibility since you're looking at the original problem you're trying to solve and not, debugging your debugging tool. And they did this and gathered all this performance insight without impacting system performance. I've got a link to the blog post here. I really recommend that you guys check these out, if nothing else on the slides. It's really interesting to see how the industry is using this, but they did some interesting stuff here in terms of getting information from eBPF about like what containers were calling what services in a way that they always had up-to-date and correct information, and they weren't like pointing at stale servers that had been shut down or anything. So it's really interesting to see how they approach this. So another case study, let me just check comments real quick. Yes. So I'll probably, I don't have a slide on this, but I'll cover this a little bit more at the end, Zeus. But using an eBPF program and letting it run in kernel space, it really makes all metric collection so much more lightweight. Usually when you're doing any sort of performance collection, you have a user space application that calls into the kernel to ask for some information. And every time you call into the kernel, it's called a context switch. And basically, the operating system has to save the state of the application that's running that, and it has to switch over into kernel mode, do whatever it needs to do there, and then it has to restore the state of the program to before it was running, and then let it continue on normally. So that's actually kind of heavy on computation. It uses up a lot of CPU usage. It'd be like 10, 15% on a given system, but it varies a lot depending on your use case and what kernel settings you have. But eBPF, what it does is that whole kernel part is always running in kernel mode. So whenever something that you're trying to monitor happens, maybe it's like receiving a network packet, that custom code runs. There's no context switch. It's just part of the stuff the kernel was doing already. And then the eBPF maps that I talked about earlier, I can't remember exactly what it was. Oh, here. So I mentioned these are like key value data stores, but really there's a lot of data structures. So it's basically just a way for that in-kernel program to store information. So maybe it's like counting network requests, and it has a counter that starts at 0. And every time it sees a new network request comes in, it bumps up that counter by 1. So that all runs in kernel space. And then if you have some application in user space that wants to check that information, rather than calling into the kernel and asking for information constantly, it just opens that eBPF map. It's just like a regular file on Unix. You need a special API to access it, but it's just a file descriptor on the system. And that's all real-time data communication between your eBPF program and whatever you're doing in user space. So that really lets you get lower overhead communication between whatever your kernel part is and whatever the custom code that you're trying to use to monitor how that works. And that's significantly faster than any traditional technique in a way that really opens up more monitoring than you'd be able to capture in the past, just because of all the performance problems you'd run into. So I hope that answers your question a little bit. I can answer more about that later. Yeah, I've got to consider it at work because we're using New Relic. We're using like more traditional agents for capturing that user data, and we're not using Pixie, even though I know it integrates with it. And I am really interested to see like what performance difference it's going to make if we just use eBPF collection for everything we can, because we have a lot of trace points. We have a lot of places where we're getting custom information around like gRPC requests. So I know we could cut down on CPU usage, and I am interested to see by how much. So one more case study I want to go over real quick, and this is around enforcing encryption. Meta, that's Facebook's parent company now, they wanted to make sure all internal traffic across their whole infrastructure was encrypted. And basically that means, when you access the website and it's HTTPS instead of HTTP, that's not the only place where you encounter encryption, but that's probably the most common one. Whenever you're accessing an encrypted connection, it's usually from like you, the customer, or the end user to your company. But your company also has a whole bunch of stuff in their own infrastructure that talks to each other. In Facebook's case, given how many services they have, that's a lot of different components and a lot of infrastructure. So they wanted to make sure all their internal stuff was encrypted too. And for anybody who's worked in the industry, it's not very common that everything internally is encrypted. But they needed to do this without impacting production services. So just setting up a firewall and having it drop all unencrypted internal traffic, that would break things pretty quickly.
Mute, guys.
Yeah. Okay, so their solution to this, Meta developed a tool they call SSL Wall, and it leverages eBPF to enforce encryption when TCP connections are open or closed. Because of all the flexibility of doing eBPF, I mean, there's other ways of accomplishing this too, but they were able to run this in passive mode at first. And this kind of like SC Linux permissive mode. Forever who has run like SE Linux in permissive mode, basically you're just capturing information around what's happening in the system. You're not really blocking any traffic yet. So this kind of let them get a heads up on what's going on in terms of like what unencrypted internal traffic is happening. And when they were ready to enforce it, gave them the ability to provide transparent TLS encryption for some edge cases. So rather than having to set up encryption on all these services that didn't have it, they would just set it up in a way that if it detected unencrypted traffic, it would take care of the encryption part and you wouldn't have to modify the app. So they successfully enforced their original requirement across their whole infrastructure. And they did this again without having to do a layer 7 firewall or something else, which is a central point of failure. I've seen plenty of incidents where somebody has broken a firewall or even locked themselves out of it, more of a traditional one. So this is a really creative approach to enforcing encryption and doing it in a way that's transparent to apps. Oh, thanks for the feedback, guys. Appreciate it. One final use case I wanted to go over. This is by Cloudflare, and Cloudflare is a content delivery network that's famous for their domain denial of service protection. Those are familiar with that. That's DDoS, domain denial of service, and those attacks are where you try to flood a endpoint or a company or something with so much traffic that they can't process legitimate traffic in real time anymore. So that's complicated when you're at Cloudflare scale because you can be under some major attacks if you also have so many customers and so many endpoints that you are like one single point of failure for probably like a quarter of the internet. So they have extreme performance requirements and they needed the lowest latency way of dropping illegitimate traffic while maintaining legitimate traffic. They did have plenty of solutions around this. It wasn't like they weren't able to handle this problem before eBPF, but those features relied heavily on proprietary network interface card features. Basically, they had special hardware that would let them do some processing before the network packets would even hit Linux to figure out whether or not to drop it. So trying to do that within the operating system using IP tables or something, that does work. IBP tables isn't necessarily smart enough to figure out what's legitimate traffic or not, but it's perfectly good at dropping packets. But the problem is it's running within the kernel, so the kernel has to receive a network packet, allocate memory for it, put it in a buffer, notify a process. It actually has to do a lot of work just to figure out whether or not it's processing a packet it's going to drop or not. So Cloudflare already had a solution for this, but they wanted one that was portable. They wanted one that wasn't tied to the network cards they were using. And they created something called L4Drop, which uses eBPF and Express Data Path, which I'll go into a little bit more, for high-speed packet filtering. Since you guys are able to see the whole screen, oops, I can type. This is a good overview of Express Data Path. So this is the whole, and I know this is kind of small text, but this is the whole packet flow for anything going on with packet filtering and packet responsing in Linux. And all of this is within the kernel. There's stuff going on at the link layer, the network layer in the kernel, protocol layer, and application layer. Express Data Path is right at the very beginning of this, and it's right before the entire part of the networking stack that processes anything to do with whether or not the packet's legitimate. So before anything has to get allocated in the kernel, before anything is set up into a queue, Express Data Path runs, and it basically just runs whatever eBPF program is hooked up to it, and that lets it detect real quickly if it's something it wants to drop or not. So, in other words, Cloudflare was able to solve their problem without ever having to rely on proprietary NIC features. They had a use case with over 8 million packets dropped per second on a single server, and they only saw a 10% increase in overall CPU usage. So by dropping them so quickly and so fast, they're able to process legitimate customer traffic and not be slowed down by all of those things that happen under the hood every time you get a network packet. So really cool stuff that they did. Yeah, 10% CPU increase to block DDoS. That's really something interesting. I'm excited to see what's going to evolve in this space, because I really don't think there was any other way of doing that without hardware. And again, there was lots of problems trying to do it with drivers. In fact, if you look at like the driver stack, you wouldn't be able to handle this even if like Cloudflare had a custom driver or something. Express Data Path is the only place in this whole stack where this code could even run, and it happened significantly before then. So I mentioned this earlier. There was an interesting article from a guy called Brendan Gregg. I'll link to some of his books at the end of this and some of his articles. He's probably done more in the kernel level observability and tracing space than anybody else. I know he was heavily involved in dtrace. He worked at Netflix up until recently. I think he's at Intel now. But his blog is definitely worth a read. And he posted a recent article suggesting that the CrowdStrike issue on July 19th wouldn't have occurred if eBPF were used instead of an in-kernel driver. It would also help if Windows had really adopted eBPF. They're still in the early phases of it. I don't even know if that's like a native thing in their kernel or if it's just something that you have to install separately. So for those not familiar, July 19th, CrowdStrike pushed a configuration update that causes driver to attempt to read invalid memory. And again, like when a driver is loaded into the operating system, it can do anything. And if it does anything wrong, if it has any sort of logical error or memory access error, it's going to take the whole system down with it. And that's exactly what happened. But a lot of the stuff that CrowdStrike does could at least partially be done inside of eBPF. We'll probably need some sort of agent that still communicates with it, but it wouldn't need a whole driver. And eBPF program can't cause the kernel to crash because they just run inside of, calling it a sandbox is a strong term. I guess it's not a full sandbox, but it's close enough to one. And on top of it, it has the verifier that runs to make sure it's not accessing anything it's not allowed to, or anything that would result in invalid memory access. So in the worst case scenario, if you really had a problem in an eBPF program, it would just kind of eat up a lot of CPU and memory. It wouldn't really take the whole server down with it. So just kind of an interesting thought here. I mean, this would probably mitigate a lot of issues that we see today, and anything running in kernel space arguably needs that extra verification. I mean, actual drivers that interact with hardware, they're not going to be able to become eBPF programs, most likely, but anything that's doing network processing, like packet filtering or security tools or observability tools, eBPF is probably capable enough to handle all of the use cases, and that shouldn't really need to be drivers anymore. So that brings us to the end of the talk. I have a link to a few books here. Again, Brendan Gregg wrote 2 of these. This has been sitting on my shelf forever, and I've still only read a few pages of it, if I'm being honest. But I have read nearly the entire contents of his original book, Systems Performance, the second edition of it. And this is interesting stuff, guys. It really goes into how pretty much all performance monitoring out there, thank you very much, all performance monitoring out there is approached in the wrong way. A lot of people spend their time looking for whatever they think is a performance issue and not relying on actual data for it. I've been in more incident calls than I can count where we're chasing after something that doesn't exist or more likely doesn't matter. So this is a really good approach to systems performance, and also goes into lots of low-level operating system components about how you should be measuring for performance and what to look for and what different things mean. If you've ever used top on a Unix system or something, and you've wondered, like, what is the buff cache memory, and what are all these different CPU parameters here? Like, what do these actually represent? I mean, idle makes sense, but there's all different kinds of parameters here. So systems performance will give you probably the best insight as to what all this stuff means, especially on Linux, but it goes in other Unix systems as well. And finally, I based a lot of this presentation on this free eBPF isovalent. They're a big player in the eBPF space. I'm pretty sure they own Cilium. I'd have to double check. But this free ebook will teach you a lot about eBPF, writing programs in it, and going into the depth of tools like BPF tool to get info on maps and data structures and such. Thank you.
Hey,
All right, so reading your question. Yeah.
I think I probably already asked you this. Do you mind giving those slides to the presentation channel when you're done?
Yeah, is that? Yeah.
If it's not a big deal, just then people can have the links.
Where's
and then
the presentation channel in here?
It's down near the bottom. I think it's near the bottom, right there. Presentation. Yep. I put mine. Put Tommy's. You don't mind throwing yours in there? And then I also asked you some questions at your leisure that I know people want to know, but also anybody can ask Michael questions.
Yeah, so we're going to take a look at the questions on here real quick. All right, so I'll just go in order. Scott, three skills to learn to do what you do. Definitely. So 3 things that I would learn. You definitely want to know Kubernetes these days. I mean, Linux is fantastic. You should probably still understand Linux before you really go to Kubernetes. Otherwise, the problems it's trying to solve wouldn't make sense. And a lot of the details you'll need to get into eventually wouldn't make as much sense. But really, Kubernetes is something you got to learn if you're going to do anything SRE related these days. I mean, it's just the direction the world is heading. Even though some people are still saying on-prem containerization, platforms are always going to be important. Second thing, I would say observability. OpenTelemetry is a great tool for this. Prometheus, Grafana, all those other open source tools. It's also good to get experience with vendor solutions. New Relic isn't my absolute favorite, but it's pretty decent. It's what I've been using for a little while at my last 2 jobs, so it's good to know. Datadog is a great one. Dynatrace is all right. There's a lot of them out there, but understanding what to monitor, the different tools used to monitor it, a little bit of data analysis just to understand, what your data is representing and how to put together a good dashboard. But that's really important for SRE work these days. And finally, I'd say scripting and coding. You don't have to do it too often, but realistically, if you want to get into the SRE space, pretty much every interview process is going to have a coding component these days. And at most companies, you will still be working on like Python and stuff a lot. So Python's great to know and Go's good to know. Oh, what was that? I think someone was off mute. Scott, you also asked, what does my workday look like? Really depends whether or not I'm on call, because the on-call person on my job handles all the day-to-day stuff that comes in. So off-call weeks, probably like 40, 60 on code and infrastructure time. Meetings, probably an hour to an hour and a half a day. Naps, maybe on Fridays, but not really. And yeah, on call weeks, I mentioned that could be a lot different, especially Fridays. We always have stuff that goes out on Friday for some reason. So usually something to fix on Friday. Paging isn't too bad. But yeah, it's a good space to be in right now. I don't think SRE responsibilities are too bad. I'd say it's still a little bit easier on the on-call side of things compared to being a platform engineer. And what do you like about what you get to do every day? I love looking into new tools. I really wish we had some eBPF tools on the horizon. Maybe I'll try to do what I can to work with that soon. But like I'm looking into a tool called Incident.io right now for incident response and PagerDuty AI ops, and it's really interesting to see what's going on for like anomaly detection in the monitoring space and alerting space. And yeah, it's good to be able to work with new tools on a frequent basis. If you're going to be an SRE, that's hopefully something you're going to have to do. So, and keep going with the questions. Awesome eBPF. I actually haven't seen this page yet, but I've seen a lot of the other awesome pages. I'll have to look into this. It's a good resource. Thank you. Linux, Docker containers, Kubernetes sort of learning path. No, that's actually exactly what I would suggest taking. I'd still say having good Linux skills is the foundation of everything. Containerization is important, but as an SRE, you're probably going to have to build containers from time to time. It is a good thing to know. Interacting with containers and managing deployments of containers and setting up service connections to containers, that's all more on the Kubernetes side of things. And I'd say that's more reflective of what SREs do day to day. The Gremlin cert. Yeah, that was a great one. I've got 19 certifications, and the one I get asked about like 70% of time is this one. People love the term chaos engineering. People think it's an interesting tool. I still haven't had the chance to use it any of my jobs, unfortunately, but I do want to look into it more one day. I'm thinking of setting up like a Kubernetes home lab environment or a small cloud environment or something, because it is one of the tools I really want to look into. Looks like there's a couple other questions coming in. I think I had one or two other things on the slide. Let me check. Oh, so these are all in the shared slides in the presentation channel. eBPF's documentation is really good. There's a article from Linux Weekly Newsletter. That's a thorough introduction to it. That's great. Again, Brendan Gregg has a lot of resources around this. Learn eBPF tracing is good for BPF trace and for, I think, PCC programs. If you want to read a lot more about BPF, the BPF type format, this is much more the lower level kernel side of things. For those of you who are more curious about how eBPF programs are different than drivers, but this goes into like what makes eBPF programs so portable in between in between kernel versions. And then finally, another good article on kernel analysis and BPF trade, again from the Weekly Newsletter. And if you guys have any questions, here's my link. I have LinkedIn. I have a GitHub account, although I've been meaning to put more stuff up on here. Not a lot of recently updated stuff, but I'll be working on that in the near future. And then I'm always available on Discord, of course. Do I feel like getting my degree was an important step or more of a personal goal? I'd say both. I mean, I feel like it's going to be important for me if I want to make a transition over to like more of a software engineering role rather than an SRE role. And it was also a personal goal because I want to go get a master's afterwards, and actually hopefully going to start in Georgia Tech next year. So I'm excited for that. So I guess, yeah, it's both personal and career goals. Yeah, for those of you not familiar, Georgia Tech has a really good online Master's of Computer Science program. That's what we'll be majoring in. It's not very expensive. There's a few other like top 10 computer science universities. I think UT Austin and UIUC, but I'd say Georgia Tech is right along the same rankings of them, and it's probably has like the widest course selection available. There's also like a number of specializations you can go into. The computing systems, there's machine learning. Did I need my CS degree to get where I'm at? No, surprisingly not. I actually just completed it a few weeks back. It was July 26th I got it, I think. So no, I made it really far without it, but I am looking forward to get into the software engineering side of space eventually, or maybe even into machine learning if I can break into there. So I feel like that will kind of open the doors for me on that side of things. As far as being an SRE or when I was a platform engineer / system administrator, it definitely wasn't as important in that space, I'd say. If you're going into security, I know it matters a lot. WGU program, was I working full time? Yeah, I was working full time. I had lunch breaks and time after work to get it completed. I pre-studied on it a lot to make sure that I would only just spend one semester there. I mean, figured I'd just save on the tuition and get it over with so I can get into tech sooner. But yeah, if you're going to get into it, there's a ton of available information on the subreddit for it. I think it's WGU.sci. And there's, you know, you could read the course syllabus for your classes. You can prepare before you ever enroll. There's a lot you can do to just, get yourself set up ahead of time. Like I read, I think 2 full books on operating systems before I started, and but myself, we spent some time getting familiar with it, Java Spring, because I know they use that a lot, and that actually helped me save a lot of time on it. So I did want to demo one other thing, and this was just my capstone for WGU. So this is Google Colab, and for those of you who know Jupyter Notebook, it looks an awful lot like a Jupyter Notebook because it basically is. It's just like a hosted version of it because for the capstone project, you have to have like a program that you can distribute to them and have them run interactively. So a Jupyter Notebook's good enough for that. There's a little bit of stuff up here I won't cover, but or these commands right here. But basically, this application is a plant species classifier. So you give it an image of a plant, and it will give you its best estimate of what species the plant is. It supports 30 plant species from just a data set I found on Kaggle. Scott already mentioned that earlier today. For those of you on that call, Kaggle is great for getting started with anything around data. So I won't go over the code I used to build the model for this, but this is just the interactive version. And this has a little part of the beginning here is just a couple shell commands to set up dependencies. I used a different version of TensorFlow for training the model than what the Google Colab latest version is, but thankfully we just updated in place. So this part right here, this is the little setup code. It grabs like the already trained model and the training history for some visualizations and a couple test files. Just uses the Google Download API to grab those, the public file. And then a little bit of code to pre-process the image. And we send everything in as like RGB and scale it down to 244 by 244 pixels. So this has already been run. I won't have to run this part, but this is what actually handles file upload. I'll give it a watermelon. And we'll see that it predicted it's watermelon. We also get a prediction confidence graph for this. And it shows watermelon was by far the best guess. Its backup options were cantaloupe and melon. To give another example, it's not perfect. The capstone is more around how well you go about training the model and the paper you write on it. But this is aloe vera and a cucumber. I could have spent all day training this model and made it a little bit more accurate, but that wasn't really part of the requirement. They just want to see, like 60, 70% accurate. And there's a couple dashboards that go along with this. I'll run this one real quickly. This is around the training and validation accuracy of the model over the different testing epochs. I said to 100 epochs, let's try to get it pretty accurate. You'll notice we didn't even peak in accuracy around there. Machine learning kind of has this spread. It probably overtrained a little bit. But yeah, this just is a cool visualization of how the model was trained. And we also get something called the confusion matrix, which shows like everything diagonal that's colored in here. These are where it's correct on its guesses. And then we get a distribution of how often it confused something. So if we look right here, there's cases where it thinks a melon is a cantaloupe, qualifies that. The program actually took me 3 months. I transferred in pretty much all my Gen Ed classes and yeah, I mean, I think I knocked out everything other than natural science lab. But yeah, like I said, I pre-studied for this a lot, and I was working for in the industry for like 6 years prior to this, and been using Linux and doing some coding forever. So it's a really good program if you're already familiar with a lot of the content. I'm sure it's great if you're getting started in computer science or more intermediate level. But in my case, like I've used a lot of these frameworks. I've done or frameworks like Spring. I've done a lot of work on like other server-side application frameworks, kind of thing, like Ruby on Rails, some other stuff, Django. So learning like all the Java classes, there's probably like 4 of those. That was really easy. I knew SQL already, so that made data management classes easy. So I would say the content of the university is great. Even if you're like just trying to get started, I found it pretty good. If you're used to a more traditional classroom model, it's not going to be great. You have to be pretty diligent with your own time management and stuff. But for somebody who's already been in the industry a while, it's a great option because there's no sense, in my opinion, spending 4 years learning something that you already know pretty well. Thanks.
Hey, Pessa.
Yeah.
What percentage of your success do you directly relate to knowing me? And then we'll just assume all the rest of the percentages is just like not directly related to knowing me. No, just kidding.
Well, Success that I'd attribute to being on that team, probably like 70%. I mean, it's hard to make the jump from help desk to being a system administrator or Linux engineer at all. But once I, finally was able to get in there and start working on stuff, and that really set the pace for my whole career.
You were worth it, man. You changed
Thanks,
a lot of things and improved a lot of things there while you were there. So believe me, I still appreciate it to this day.
Thanks, man. I really appreciate that. I miss being there. I actually kind of miss even like the time I joined the SRE team. It wasn't as fun over on DevOps. I liked it on the operations side.
Yeah, it's hectic and absolutely terrible when you're doing it. It's like being in the army. It's like it sucks while you're doing it, but you miss your buddies when you get out,
Exactly. Like,
Yeah.
I don't miss the 16-hour days doing
Yeah.